Thank you. Thank you very much. Thank you for being here. So wonderful to have you here. I'm so glad to be here in this room with you and having the opportunity to deliver this information once again. And I'm real excited about it because I've got a whole bunch of new stuff to talk about. So I'm going to kind of walk you through a little bit of the way I discovered this information and the way I came across it, my logic through it, and the path I took. And if I walk you through the same path I took, you'll see that it actually is a very simple path. It's a very simple way of thinking. It's very fundamental and very simple axioms that just needs very little adjustments in our current physics and science and so on to generate just a little bit of a different picture that opens doors to a whole new way of being. And so, although this information may seem quite complex, it actually, is very accessible to everyone. And I teach this to 7 years old and to 80 years old, and everybody can get it. So keep your mind open, keep your heart open, and we'll go from there. So it really started when I was approximately 9 years old. I could have been 10 or 9, but I remember very distinctly this first lesson at school. And interestingly, I found that many other people had the same kind of hick when they got into this first lesson. It was the first lesson in geometry. And the teacher went to the blackboard and said, today we're going to learn about geometry, and the first lesson in geometry is dimensions. And I got really excited because I had all these incredible world that I was living in my head, and I had all these interaction with all these other dimensions in my head, and I thought, oh my God, this teacher is going to talk about this for the first time ever. I'm going to have an adult that talks about this, and I got really excited about it, and I got so disappointed. It wasn't at all what I expected. The teacher went to the blackboard and made a little dot. And he placed beside the dot dimension 0, 0D, and said this is a dot that represents a dimension that does not exist. And I was already confused. I'm like, oh my God, this is not looking good. I'm probably gonna fail this class because I could see the dot, and he was telling me that it didn't exist. And so already I had a problem with that fundamental axiom, and really this is so crucial. This is so crucial to our understanding of reality. This very fundamental axiom of dimension bleeds into advanced physics, advanced mathematics, and all sorts of sciences, and really changes the picture of the way we see things if, it's not accurate. So I didn't know all this, but I thought, well, I can see the dot, but if you say it doesn't exist, I'll just go with that. And then he said, well, because it doesn't have volume, it doesn't exist. So if you put a bunch of dots together and make a line, you still don't have volume. We'll call that dimension 1. And that doesn't exist either. And, I just kept on going with it. And I could see the other kids in the class were a little bit puzzled about what was going on. And then eventually, he put 4 lines together to make a plane, called it dimension 2, and said that didn't exist either. It still didn't have volume. It was a 2-dimensional flat plane. And, you know, I could see, he used the example that the cartoons in our cartoon books didn't exist, right? And so I could see a lot of the kids were very disappointed. And then he did something extraordinary, something miraculous, something that even puzzled me further. He took 6 planes, put them into a cube, and called it 3D, and said that dimension exists because it has volume. And I could see that everybody was like, okay. There was a problem in logic there. Turns out that I found out much later that Buckminster Fuller had exactly the same problem in its schooling, in his first lessons in geometry. There was a problem there because if you have a dot that doesn't exist, that makes a line that doesn't exist, that makes a plane that doesn't exist, then you cannot get existence out of 6 non-existing planes. So what you get is some unknown feature that could only be called non-existence to the 4th. Not existence. And so here, fundamentally, there's an issue. And that issue has to do with our understanding of how reality emerges, how dimensions are generated, and how we can get existence, reality, atoms, objects, things in space, and how we solve the equations that describe how these things in space come through, how they get here. That is very fundamental. I didn't know all this at the time, but I knew that this principle that was being demonstrated to me was not quite correct. There was definitely improvements that had to be done to it. And I really felt like I didn't want to spend another day going through my life not knowing what a dimension was. So I decided I was going to solve this. And, you know, I had this long bus ride going all the way back home. It was like an hour and a half from that school. And the reason for that is because I kept on getting kicked out of the schools that were closer to my home. So I kept on having to go further and further. And somebody told me, a physicist told me once, that I was furthering my education that way. And he was right, because I had all this time to think in the bus. So I was in the bus and I was thinking about this problem, and I decided I was going to solve that problem before I got out of that bus. And I didn't realize that this problem had been discussed and worked on by many philosophers throughout the ages and so on, all the way down to the Pythagorean schools. I just wanted to solve it right there and then. And so I was thinking, and the bus was getting fuller and fuller, and I was getting hotter and hotter, and it was really, you know, becoming uncomfortable. So I closed my eyes, and in my mind's eye, I escaped the bus so that I would feel more comfortable. And I start to see that the bus would, as I rose above it, the bus would become a dot. And then I rose further, and I saw the Earth becoming a dot. And then I rose further, and I saw the solar system becoming a dot. And I rose further again, and I saw the galaxy becoming a dot. And then I started to fly back into the galaxy, into the solar system, back to the Earth. And I located the bus I was in, and back into that bus, and back into my body. And I opened my eyes, and I looked at my hand, and I thought, oh, maybe I could fly into my hand. And then so I closed my eyes again, and I thought of flying into my hand, and I saw that inside my hand would be dots that are called cells, and then inside those cells I would see millions and millions of other dots that are called atoms. I probably didn't even know what an atom was at the time. And I continued in and I saw, the nuclei of an atom that was made out of smaller dots and then again smaller dots and so on. And I thought, and then I got it. I had this moment of illumination. And then in the bus, going back from school, oh yes, the only solution to this riddle, the only way you can solve this, the only way you can, the only way you can visualize, understand dimension is if you make the exact opposite axiom right from the beginning, which is that the only thing that exists is the dot. So here, within the dot is all dimensions. Within the dot, we have all the structure of space-time. Within the dot, all possible other dimension became in existence. That's the way I saw it, meaning that if we continue to divide the dot, we could find smaller and smaller and smaller dots, and those would be like scales of dimensions. And that the only thing that exists is the dot. And it is only from your perspective that you define the scale at which you observe those dimensions. I mean, that was a completely different view, definitely. And I thought, well, if the dot, if zero dimension is all dimension in one, then that would mean that everybody that I'm looking at in this bus has all the dimensions, all the structure of space-time compactify in every dot. I mean, I wasn't thinking in terms of space-time, but I was thinking in terms of fractal dimensions. I didn't know fractals, but I had defined it in my head. And I got really excited. I was walking on a cloud. I got up in the bus and I didn't know what to do. I was like, oh my God, I think I got it. Everything is a dot. Every dot has infinity within it. Everything can be divided to infinity. And there's dots to infinity, infinitely big, infinitely small. We're living in a big dot that has little dots in it and little dots in it. And I was seeing dots everywhere. It was really exciting. And when you have a revelation, you want to tell someone, right? So I didn't know who to talk to. I wasn't going to talk to the bus driver, and so I ran home when I got out of the bus, and I was waiting for my mom to get back from work. And when my mom came in the door, I'm like, Mom, I figured out something at school today. It's really exciting. And, my mom was so excited because she thought, oh, my God, you finally are doing good at school. Oh, my God. And then I started to tell her about this. And I'm telling my mom, I think you have a dot inside of you that has all the dots and infinite dots inside and all this. And my mom is looking at me with a look of despair. The look of an Italian mother in despair. There's a force in that hasn't been calculated yet. And so she kind of could see it, but she knew it wasn't part of my curriculum at school, and she told me that. And she said, if you answer that in your exam, it's probably not going to go well. And she said, anyway, right now, I just worked 8 hours, and I don't feel infinite. And when she said that, it rang a bell. I mean, she made a point. She made a very important point. I stopped, and I had to think about it. It's like, well, if it's true that infinity is compactified in every point, how is it that we have finite boundaries? How is it that things are not just falling into each other to infinity? And how is it that things exist? How do we define those boundaries? How do we have a finite space in an infinite potential? How can that be together? I didn't know at the time, but actually I was tackling one of the fundamental difficulties in advanced physics. The difficulty of dealing with infinities and singularity, which is really the crux of unification at this time. It took me back. I had to think about that one. I was like, oh, I got to go back to the blackboard. I got to think about this before I talk to anybody else. But eventually, it came to me. And it took a very long time. I was much older by the time I realized. But all the way through my childhood, there was a few things that came through to help me deepen my belief that I had found something very crucial. Was I the first one that came to these conclusions? Have these ideas been around before? Absolutely. Okay? Other people have thought about this. Even our, Big Bang Theory says that everything came out of a point the size of a Planck's distance, which is extremely small, billions of times smaller than an atom. These ideas have been around. Have they been well understood? Maybe not. Certainly, I think some of the masters and some of the advanced beings that have walked the earth may have understood them. In terms of physics, in terms of advanced sciences, it's been thought about, but it hasn't been mapped out. It hasn't been understood in its detail in order to be able to apply it to our current physics and our current math. Why would we want to do that, though? Well, we would want to be able to if we want to be able to understand the fundamental structure of creation, and that fundamental structure implies or involves infinities and finite boundaries all at once, we have to find a way to bring these two together, to understand their interaction, to understand how that works. And if we did that, and if we did so, we would have the key to universal forces. We would have the key of the powers of creation. It would be very powerful. It would be powerful for philosophical reason, and it would be very powerful for application to advanced science and technology. Now, it took me a while before I realized that there is a direct and intricate link between infinities and finite boundaries, and how to understand them and how to demonstrate it. I found eventually that the key was geometry, the very thing that got me going in the first place in my geometry lessons. And I'm going to demonstrate to you right now, in very simple terms, that you can create infinities in the confine of a finite boundary. That these are not opposite concepts, but they actually are complementary. There is infinities to create finite boundaries, and there's finite boundaries to create infinities. And in order to demonstrate that, I'm going to use a very simple initial graphic. Although this graphic is simple, it is still absolutely accurate to the geometry that we will see throughout the day today. It's not something in left field. It's something that's very important. So here we're going to do this. We're going to generate a finite boundary we're going to call a circle here. And this circle could be a 3D sphere that contains a very specific space. And in that sphere, or in that circle, we're going to put a triangle, an equilateral triangle. Now, the universe is polarized. And the reason why things are polarized is because they spin. Okay, things in the universe are polarized because they spin. And angular momentum creates shafts of rotation that generates polarity. So if you have polarity, then you can accurately have a reverse triangle in that sphere or in that circle. Now, right away, we have one of the most common ancient symbols that we find all around the world. It's called the Star of David, or the Seal of Solomon, or the six-pointed star. We'll talk about this later on in the presentation, but just take notice of it. Now we can continue to add triangles. And now we get smaller stars, baby stars of David. Okay, baby six-pointed stars. We can continue to add other resolution of stars by adding more triangles. Again, smaller stars of David. Every time we create a new resolution, we can define a very specific boundary. This is very important. And here we find a third boundary, so smaller and smaller sphere. We can continue to make smaller and smaller resolution of this geometry. And in fact, if I give this to my computer as a computer code, and I got it to make geometries maybe 5 resolution deep, and then zoom in, and then go 5 resolution deep again, and then zoom in, and then keep doing that, it would continue to do that to infinity. As long as the computer had power and chips would keep working in there, it would continue to make boundaries for thousands of years. However, I would never, ever, ever exceed the first boundary that I've set for myself. Within a finite system, I've demonstrated to you right now that you can create infinite numbers of division, infinite numbers of sets of information. In a boundary is the possibility of infinite division, and thus infinities and finite structures are complementary. Why is this important? Well, if you were taking these principles and applying them to yourself, you could start to visualize, you could start to imagine, you could start to experience that maybe within the confine of the finite structure that you're in is the potential of infinite division, the potential of infinite amount of information. Philosophically, that has a very powerful impact on someone's consciousness. It just happens to be very similar to what many of the masters that have walked the earth have talked about. That within is God, the kingdom of heaven, infinite boundaries, and so on, or infinite potential, and so on. It definitely has an impact on science. Why does it? Well, I'll give you an example. When we discovered biological cells, we had microscopes that were at the maximum of the power of amplification that we could get at the time, and we thought, my God, this stuff is so small, it's gotta be the smallest thing that the universe does. And then we discovered an atom. And there's billions of atoms in every cell. That is extremely small. And we thought, oh, that's gotta be the smallest thing the universe does. And then we discovered protons and neutrons in the center of the atom. We discovered the nuclei of an atom, and we thought, that is so small. That's gotta be the smallest thing the universe does. And then quarks and so on. And what I'm saying here is that every time we find a new boundary, we think, that's it. We found the fundamental structure of creation. The universe goes to that size and then quits. That's it. I'm done. I'm not going smaller. This is way small enough. We did exactly the same thing in the other direction, right? We thought, oh, you know, at first we thought the Earth was the biggest thing, and then we thought the solar system was the biggest thing. Then we found galaxies. Oh my God, that's got to be the biggest thing, right? And then we found superclusters and so on. Now we're at universal size, and we think, okay, that's it. It stops there. Right? Well, what if it doesn't? Now, what does it mean to the physicists? Well, it means that we've been building accelerators to break particles into smaller and smaller and smaller bits. And now we're at like billions of times smaller than an atom. And we're calling these accelerators, I mean, they're serious pieces of machinery. The one that's being built in Switzerland right now, the Hadron Collider is costing $300 billion. It took 5 countries to flip the bill for that one. And now we're looking for the X bosons and mini white hole black holes. And I'm like, well, at that point, you're dividing the vacuum. And basically, what I'm saying here is that instead of looking, and I'm not the first one that have said that, famous physicist Jeff Chu said it in the 70s, maybe instead of looking for a fundamental particle, we should start looking for a fundamental principle of division. And that's what I came to, is that instead of looking for a fundamental particle, we should start looking for a fundamental pattern of creation. Because if we understand the pattern, then it doesn't matter at which resolution we are observing the identity. We understand the principle behind the identity. Now we have the key to creation. And that would change a lot of things of the way we do physics and the way we think of the universe and how it creates and how it subdivides. I was really excited about this. I started to really study physics. I started to look everywhere to find how things work and where standard physics was at the time. Where did we go, and where did we go wrong, and what needed to be changed to make it do that, to make it look that way, so that we could find that fundamental structure of creation. I was determined that I was going to find this in my lifetime. It was a big mission, you know. And so I went at it, and I started to study a lot. And now we're going to jump forward to me in Georgia Tech. I'm at Georgia Tech, Department of Physics, with the director there and other physicists. And this is an impromptu private meeting discussion with those guys. And basically my sponsors at the time brought me there to measure up with the biggest and most respected physicists, some of the biggest and most respected physicists in theoretical physics. And, you know, I'm there and they have equations everywhere and we're talking about things, and it's a very small meeting, you know, but there's a few students and there's a bunch of physicists there, and there's me. And the only thing I got with me is this book. It's called Gravitation. It's like the Bible of relativistic physics. And it's called Gravitation because when you pick it up, you know, you can really tell gravity is acting upon things. And I was, you know, going through the equations with them, and I'm talking about all this, and I'm really, you know, going through it with them, and I can see that there's a certain amount of irritation and there's a certain amount of impatience with me because I'm asking very simple fundamental questions, and everybody there is doing very advanced, you know, string theory physics and all this, and you know, I'm always going back to like some fundamental things, and they're like, my God, what is this guy doing here, kind of deal. And, you know, and so at one point, I pulled out my book, Gravitation, and I said, okay, after all these equations, which is a few thousand equations, on the metrical structure of space, and then applied to the universal size and so on, the model of our universe at this point, and correct me if I'm wrong, is that the universe is expanding like a balloon. And I opened the book on page 219, and I pulled it out, and I said, here's the picture of what we believe the universe is doing right now. It's expanding like a balloon, and the balloon has little pennies glued to it, and the pennies represents galaxies. That's the standard model. And the galaxies are moving away from each other as the balloon expands. And everybody's like, yes, Nassim. Where are you going with this kind of deal? Like, if you don't know this, go back and study, come back in a few years. And at one point, well, I'm saying, well, okay, I understand this principle. However, I have a question. Out of all these equations everywhere, what I want to know is where is the equation that represents who's this guy? And the whole room became really silent. And I could see that in the look of the students and the other physicists that there was a look of despair and stress because sweat was a little bit beading. And I could tell that they got worried because they thought, oh my God, this guy, he might just start talking about God, and we're at Georgia Tech in the physics department. We can't do that. and I reassured them very quickly. I started to draw, and I said, well, you know, let's draw the rest of the guy. And what I'm trying to point out here is that in order for the balloon to expand, then the lungs of the person that's blowing into it have to contract. For every action, there's an equal and opposite reaction. Okay? One of the first laws of physics. So if our universe is expanding, then there must be something contracting, there must be some compression happening in order to get expansion. There must be a feedback between the expansion and the contraction. And that was my first clue to the relationship between the gravitational field and the electromagnetic radiation. And as well, it applied to my experience in life, because really this is all based on my experience in life. When I was 11, I started meditating. My family came in contact with a young master of meditation that was 14 years old, and I was 11. And he taught me how to meditate, and when I meditated, it felt like I was turning my senses inwards and going towards the center of my existence. I was going towards the middle of my being. And I came, out of that, I found a logic in which there was an internal universe and an external universe. There was something going in and something going out, and the two generated boundaries. And that boundary is what we experience as reality. The thing is that in our society, the tendency is to spend a lot of time analyzing what's out and very little time analyzing what's in. Not only in our, social morphs, but as well in our physics and the way we do things. We explode things. That's how we build technology. Our concept of advanced technology is to put a bunch of fuel in a cylinder, put a bunch of people on volunteers on top, and light the bottom and see if they survive the experience, It's all based on expansion, on explosion, on radiation. Very little is based on contraction, on going towards the center, on implosion. And to me, there had to be a direct relationship. So I was really pointing that out. And now we're going to go back to when I was younger. And when I was thinking about that, I could see that this relationship would generate some kind of field equation, would generate some kind of metrical space that I could describe in mathematics and physics that would resemble more like a feedback of creation. Well, just happens that the fractal structures that I was talking to you about when you divide space are based on feedback equations. I went to my first chemistry class. And can everybody see this? And the first thing I asked in my chemistry class is, I want to know what an atom is. The chemistry teacher said that was not in the curriculum of my first chemistry class. And he said that would be a physics question anyway. And as far as I know, we don't quite know exactly what is an atom. And that was quite disappointing for me. But he knew something about atoms. He said, there's one thing we know about atoms, that they're made out of 99.99999% space. And that kind of blew my mind. I was like, wait a minute. So what we see as creation, all the things we see, are mostly made out of space. But they don't feel very spacious. I mean, it's pretty solid. But what's going on is that there's all these fields interacting, and they don't necessarily are in perfect resonance and they make boundaries and so on, and so it feels like it's solid, but it's mostly space. It's basically a field dividing the vacuum. And I thought, oh, there it is. It started to match, and that was my first chemistry class. It started to make sense. Oh yeah, maybe we should look at the vacuum. Maybe it's the vacuum, what we call space, that has the key to creation. And the space divides itself, and then we see it as finite boundaries. Maybe the space is the infinity, and the boundary is the finite structure. The field is the finite structure. I started to see it in my head. I got very excited. And later on, I studied vacuum and, understanding of quantum theory, and I realized something. I realized something very important for the evolution of the thoughts I was having. I found that present-day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formally be infinite, if not removed by renormalization. Now, renormalization is kind of what they tried to do to me at school. It didn't work so good. But what it means is that when physicists start to look with the tools of quantum theory at subatomic particles and nuclear interaction and all this, they found that in order for this to be happening the way we see it happen, the vacuum density at the quantum level would have to have infinite amount of energy. That was the result of the equations. Well, equations that ends with infinity are very uncomfortable for physicists. There's two kinds of technical words in physics to describe infinities. There's one that's infinities that are normal infinities, and that's usually an infinitely small quantity. Two infinities, right? One is an infinitely small quantity, so it can easily be discarded, right? It doesn't really matter. 0.0000 somewhere down there doesn't matter. Okay? That's one kind of. Then there's another very highly technical term you find in physics documentation called nasty infinities. Nasty infinities are infinitely large infinities that creeps up in your mathematics, in your equations, in your conceptual physics. And those are thought to be nasty because when they creep up, it's not like you can just make like it's not there. It's an infinitely large quantity. You can't just sweep it under the carpet and like avoid the whole thing. Well, they did a real good job at avoiding this one. But in general, it was not accepted as a valid theory if your theory breaks down into infinities at its results. And so instead of discarding the concept, they did something that they call renormalization. They used the infinite potential of the vacuum and basically took the Planck's distance and took the 10 to the, was 1.616 multiplied by 10 to the minus 33 centimeters. So that's a very, very, very small dot. Notice, though, that the 1.616 is very close to the 1.618 of the phi ratio. And they took that distance, like that very teeny point, which is now billions of times smaller than the nuclei of an atom. And they said, well, that is fundamental to creation. And if we put the number of these little dots in a centimeter cube of space, of vacuum, we will have a finite density for the vacuum fluctuations, for the vacuum density, the energy in a vacuum, in a centimeter cube of vacuum. So here it is. They took a centimeter cube of vacuum. They took a Planck's distance bitty teeny point, and they stacked them into that cube, and then calculated how much density of these quantities would there be in there to get a finite number. The result is 10 to the 94 grams per centimeter cube. 10 to the 94 grams of centimeter cube. That's 10 to, with 93 zeros, you know, following it. It's an extremely large number. When I'm dealing with a number that large and it came from a renormalization, my tendency is to think that we're talking about infinities. Okay? Because if you want to get an idea of what density that means, imagine you have a centimeter cube of space that has all of the stars in the universe condensed into it. Like all of the stars we see with the Hubble. Okay, all the galaxies, everything we see, we just put it all in a big trash compactor and we just squash it all up into a centimeter cube of space. All right? Imagine how bright that would be in one way, but never mind that, then you still wouldn't have the vacuum density. You still would be short from the density of energy that is calculated to be in the vacuum at the quantum level. That is a lot of energy, folks. And so, how did this infinite amount of energy divide and create subatomic particles and atoms? To me, that was the question. To me, maybe the vacuum energy had structure. Maybe the vacuum energy wasn't just a random fluctuation like this, but had a boundary fractal structure, had a geometric structure to it. I didn't know why at the time. I didn't know how I could prove that. I didn't know how I could describe that. But I wanted to explore that thought. I started to see that maybe, just maybe, everything we see in the universe is just division of that energy density of the vacuum in various scales. To me, there was some logic to it. Well, that brought me to eventually a meeting with Elizabeth Rauscher and a collaboration with her. Elizabeth is a very respected physicist that has received medals of honor for work in black hole physics in the 70s, has worked with John Wheeler, many other very famous physicists. And Elizabeth and I got together, and Elizabeth had written very advanced computation and mathematics for a unified field theory in the 60s and then in the 70s. And she could never kind of get the whole key put together. And, you know, when we met and I talked with her for almost 3 days, I was able to fill in a lot of things, but she didn't know, and we had to talk some more, and we had to run some calculations and all this. And she was definitely skeptical, but we started to write things, and then we thought, well, okay, if this is true, then if we look at a large scale in the universe, we should start to see very specific divisions. We should start to see structure. If the vacuum is dividing under very specific structure, then we should be able to see it. We should be able to calculate it. from what we observe. So we decided to write a scaling law. And this is what came out. This is a paper that's unpublished at this time. I'm publishing other papers in the scientific journals right now that are the foundation of the change I've made to Einstein field equation. This will follow. We presented this at the American Physical Society in Albuquerque, and here and I've presented it as well to some of the directors of the telescope here on the Big Island, and many other astrophysicists and physicists. And usually I get a pretty good reaction out of it. It's kind of, you know, jaw-dropping. What we did is we took the radius of objects, okay? And so here on the in the x-axis is the radius. And here is the frequency of these objects, the fundamental frequency of these objects in hertz. And the energy level of the object is pretty well described by its frequency. So you could think of its energy level as well. If you take the size of the universe, that is, if you look at the way the universe is expanding, you can extrapolate its size. And if you look at all the matter that's in the universe, when you place that amount of density, when you place all that matter in Einstein field equation, the result is that the universe is too dense for light to escape it. That is, we live inside a black hole. And, you know, that was expected from me. I thought that earlier, and then I realized that as well from my own calculation before, and I thought that would make sense. Because remember, I was thinking that if for every expansion there's an equal and opposite contraction, then everything can be divided to infinity, then everything would have infinite density at its center. Everything would have what we call singularity at its center. And so I thought everything is just a different size black hole. And so I wasn't surprised about this. So we placed the data point for the universal, the 10 to the minus 17 is the universal frequency based on our calculation, and the radius is 10 to the 28. And then we place the next data point for quasars. We're taking average size and frequencies of quasars. This is a very large scale, so it's acceptable. And we place the data point. And it surprised us. It was a fairly good linear progression from universal size. Then we place the data point for galactic centers. So we're getting smaller in scale. And again, an average galactic center oscillation rate and radius. And we place the data point, and again, linear progression. Then we place a data point for solar dynamics, stellar dynamics, and we got a linear progression again. That was astonishing. I mean, there is nothing in standard views that would predict that, other than the view I was getting that the vacuum is dividing itself under very specific structure boundaries. Then we went all the way to the atomic level with the radius and fundamental approximation of frequency for X-ray emission. And we got a data point that was a perfect linear progression again, but this time across the boundary of quantum theory into the atomic level. So now we went from cosmological object to quantum theory level. And this is one of the fundamental fracture in our current physics. Quantum theory and relativistic physics don't agree. They don't work for each other. So that was really exciting. And then we went all the way down to the Planck's lengths and placed the Planck's length dot data point and at 10 to the minus 33. And sure enough, the progression was perfect. And that got us very excited. I mean, definitely it supported what I was trying to explain to Elizabeth and our discussion, and we started to really get some steam going, and it was really exciting to see that happen. And we thought of publishing it, but I wanted to publish first very fundamental physics to be able to explain this, not just the phenomenon. The other thing we noticed is that if you take the distance between the data point, which is kind of nice, it's sweet, and you divide them, you always get very close approximation to the phi ratio. The phi ratio is 1.618 and is, and goes to infinity. It's typical to find it in nature everywhere. You find it in flowers, in shells, in pine cones. You find it in the way tree divides. You find it in your body. There's a phi ratio between the end of your finger and the second part of your finger, and there's a phi ratio between the second part and the third part and your hand relative to your fingers, and then your fingers and hand relative to your forearm, and your whole body is built like that, and so on. And so you find it in nature everywhere. So to find it on a scale that's so large was very exciting, because it supported that this would be something that nature would naturally do, that space, that the vacuum would naturally divide itself under these very specific fundamental mathematics, because we observe it in nature everywhere. And so it confirmed to us a lot of it. Now, this was my presentation at Albuquerque, and I'm going to add a little data point for our benefit here. I didn't do that there because it could you could freak out a few physicists. So the physicists in the audience, please don't freak out. But if you actually add a data point for the biological resolution, what I call the biological resolution, that is the size of the sphere of our cells and their frequency level. Now, this research has shown that there's definite resonance match at approximately 10 to the 11 for the frequency of lipoprotein of the boundary of cells. So that means the cell's boundary, all right, the surface of cells in the biological level oscillate at 10 to the 11 hertz. I mean, that's a massive oscillation. And it's funny because when we think of biology, we always think of some really kind of glooby, kind of blobby thing that's moving really slow, right? But actually, the surface, when you look on the surface oscillation of these cells, it's very intense, a lot of energy. And it just happens that if you take 10 to the 11 hertz and you take the radius of a cell and you apply that much energy into that radius, if you solve that with relativistic physics, the cell obeys the Schwarzschild condition. That is, the cell obeys the condition of a black hole. Okay, I'm not, don't panic. It's okay. But what I'm saying is that we're still dealing with the same fundamental dynamics, even at the biological level. And certainly, there's not any biology in Einstein field equation, and there's no biology in quantum theory. And, this link to biology has been looked for a very long time. Well, we were happy to find that if you place that data point for the biological cells on the graph, it would bisect the graph approximately in the middle of the graph. That is, the biological resolution is the link between the large and the small. You are the event horizon, loosely termed. And you are the data transfer boundary from the extremely large to the extremely small. Isn't that what you do? You gather information and transfer it to your internal self, which in this view has infinite boundary potential. Thus, you're transferring that information through your boundary to the infinite of the universe within yourself. And as you start to see yourself grow into that world, your worldview, your way of being in the universe, the way you are, how you are, completely changes. Because you start to see the importance of your observation. You start to see the importance of your interpretation of the field and what you are feeding the universe. Instead of seeing yourself as an insignificant little dot that means nothing to the universe, you start to see yourself as the center of creation. Now, you might think that's arrogant. I think I've heard something along those lines from the new Pope or something. But I would like to say that if you have come to these conclusions, you must have come to these conclusions finding out that everyone else is the center of their universe as well. And thus, we are all equal and we're all one. But beyond the philosophical views, the fact that the biology would fit on this graph, the fact that we could start to see the information feedback loop between the radiative side and the contractive side starts to open a whole new field of physics. For 20 years, and you know, I've been saying this for a long time, I've been saying that information doesn't just flow into black holes, but flows out of black holes as well. And I got in a lot of trouble for that. And it was nice to see that just recently, Stephen Hawking has made a public announcement that he now believes, after 15 years of refuting this, or 30 years of refuting this, that black holes have information radiating out, coherent information. Before, they only had Hawking radiation, which was thought to be generic and incoherent. So now this is actually coming to the forefront. It's very exciting for me because finally I feel like there is some support. It was very recently that these announcements were done, and as well, to me, it was clear a very long time ago that if this was true, then the center of all galaxies had to be black holes. So I predicted that, and then eventually they found that that was the truth, and although I got in a lot of trouble for saying that early, and so on. And so I start to see the infinite potential of everything present in everything. Okay, so now we've got divisions in the vacuum. What dictates those divisions? How is the vacuum structured? If the vacuum is divided in very specific ways, then it must have very specific division structure. Then the vacuum has structure. How can that be? And what would be the structure? I wanted the key to the equation of vacuum division. I wanted the key to the creation of these boundaries. Because if I knew the key, then I could create one of those boundaries. Now, let's go back in time a little bit, and I'm in high school and I'm not doing so good. I'm still not doing so good in the educational system, and it's funny because my father worked with Piaget and is well respected, child psychologist and so on. And he had all sorts of trouble with me. And at the age of 16, I'm done with the whole thing. And okay, if I have to live doing something else, then that's what I'm going to do. And I decided, since I was a good skier, to become a ski instructor. I was in Alberta at the time, and then eventually in BC, in Canada. And I'm getting tired of it because I'm freezing every day. And I'm tired of freezing every day. And I want to do something else than sit on a cold chairlift. So at the end of one season, I decide, listen, I'm a good scuba diver. Maybe I should try teaching scuba diving in the summer so I don't freeze all year round. So I opened the map and I just pointed. And my finger landed on this island called Isla Mujeres off the coast of Cancun in Mexico. And I pulled out my English-Spanish dictionary and translated Isla Mujeres, and it said Island of the Women. And so I was a ski instructor, so I was like, oh, I'm there, So I got to Isla Mujeres and I started teaching scuba diving, and I'm having a good time, and I get a few days off, and it's like, okay, let's go and visit, ancient sites and stuff, something. So I get out there in the buses with the pigs and the chicken and everything, and I'm going through the jungle, and then I come upon these pyramids, Chichen Itza, just out of the jungle, these huge pyramids sticking out, freaky. And I, went and visit, and so I'm taking pictures of the pyramid, and I climb up the stairs, and at the top is shaded, so I'm happy to get there, and I'm sitting in the shade, and I'm kind of doing a little meditation, try to feel something. And I hear, tour guide coming up and with tourists. And I'm listening to what he's saying in the background. And he's talking about how these people move these stones from the quarries that are miles away across the mountains and down and so on, and then brought those stones and put this pyramid together, and how they use copper tools to carve it and all this stuff. I'm listening to all this, and it's freaking me out, because it's like, I remembered the lessons I had at school about antiquity and so on, and the pyramids of Egypt and so on, and how improbable those theories seemed to me. But I'm listening, and he's talking about cutting stones with copper tools. I know that copper doesn't cut stone and so on. And I'm having a really hard time with this whole thing, because I'm looking at the dense jungle around me, and I'm like, wow, how did they get those rocks here? And then he talks about how precise this pyramid is and how it's aligned to the solstice, so that when the shadow hits the corner of the pyramid on that very specific day, it casts a shadow that generates the body of a snake going down the stairs with the head of the snake carved at the end. I've got a pretty good notions of engineering and astronomy and so on, because I've done a lot of study in that, independent studies. And I'm listening to this, and I'm thinking, whoa, man, this is not easy. You can't just whip that out. Or you can't, you can't just have the pyramid built and then, like, on the right day, just get Joe to pick it up and align it. Little bit to the left, Joe. That doesn't work. Can't do that. So I'm listening to this, and I'm kind of confused, but I'm interested. And then I start to think, well, wait a minute, I'm looking for a fundamental structure of creation, and there's these buildings, these pyramids, everywhere around the world. And I'm thinking, well, why are they all building pyramids? Why did the Egyptians, the Mayans, the Incas, all these people are building pyramids? What's with pyramids?
Thank you for joining us today in Crossing the Event Horizon. Nassim Haramein's research is supported by the generosity of the public. To directly participate in this most crucial work, see our website for more information on how you can stay involved by visiting www.theresonanceproject.org. Thank you for continuing to spread the word about this exciting work and recommending this DVD to your friends and family. Be sure to watch the special features portion of this DVD.